Let us recall that we ended the last video with this lemma 6.10.4. Let's just see the statement once more. So T is a linear operator on this finite dimensional inner product space V. Then we have to prove that T star is also a linear operator on V. That means T star also belongs to this operator algebra. Moreover, for any two such operators S and T on V and any scalar lambda in F, the following are true. If you take the Hermitian adjoint of T 2 times, then you get T back. Also, we have this, that the Hermitian adjoint of S plus T equals the sum of their Hermitian adjoints. In number 3, we have this scalar multiple of S by lambda and its Hermitian adjoint, that equals the complex conjugate of lambda times the Hermitian adjoint of S. And finally, here we have the product of S and T and its Hermitian adjoint equals the product of their Hermitian adjoints, but the order gets reversed. So let's now prove this. In the proof, we are first of all going to show that T star is a linear operator if T is a linear operator. And for that, we will first show that T star respects vector addition. So let us take two vectors V and W in V. But of course, after that we also have to show that T star respects scalar multiplication. So here itself we also assume one scalar lambda. Now for any u belonging to V, let's consider this inner product where one vector is u and the other vector is the T star image of V plus W. Okay. Now by the definition of star, if you go back in the previous video and see the definition of star which arises from that lemma, if you remember, then this equals the inner product of ut and V plus W. If you write like this T star gets transferred to this first vector and becomes T. You can think of it like that. And then by linearity, this equals the inner product of ut and V plus the inner product of ut and W. Alright. And then again you apply the same thing and bring T back to the second component. It again becomes T star. U comma Vt star plus U comma Wt star. And again you apply linearity and get this. The inner product of U and Vt star plus Wt star. Because this is happening, that is, this inner product is equal to this inner product for all vectors u, see, any u. That is why this should be equal to this, again by that lemma and by the definition of star. So that's how we have the fact that T star respects vector addition. Next, we are going to show that T star respects scalar multiplication. Next, for scalar multiplication, we consider this. So we take the scalar multiple of V by the scalar lambda and apply T star on it, and not just that, of course, we consider this inner product of that and u in this order. First u comes followed by that one, and then again, as usual, we transfer this T star to the first component, it becomes T. So that way we get the inner product of ut and lambda V. And then lambda will come out, but because it will come out of the second component, it will not itself come out, but rather its complex conjugate comes out, lambda bar times ut comma V. And then again you transfer this T over to this second component, it becomes T star again. So it becomes lambda bar times the inner product of u and Vt star. And then again you push this lambda bar inside. It becomes lambda because we are pushing it to the second component. So that way we get u comma lambda times Vt star. Note that we have carefully placed this thing together. That is, we are multiplying this entire thing, this entire vector by lambda. That is why those brackets. So then this equality happens for all u, because u is that any u, and that is why again just like that calculation, this equals this. So isn't this the fact that T star respects scalar multiplication? Yes, because the T star image of lambda v equals lambda times the T star image of v. So that is why combining this and this, you have the fact that T star is also a linear operator on V. That means it belongs to this algebra. So next we have part 1. For part 1 we have again started by considering these things. If you want you can continue this, but I have decided to do it separately. So again I have taken V to be any vector in V. And then for any u belonging to V, you consider this. By now you know what to do, how to start the calculation. The inner product of u and the T star image of V. So if you transfer this operator over to the first component, it loses that outer star, but still the star that you have inside stays. That means the inner star still stays. You treat this T star itself as an operator. Note one thing carefully, that we are able to do this because we know that T star is itself also in A of V. Just like we have T in A of V, that is why we are able to transfer it like that. Okay. But from here you cannot really do anything. I mean, if you have the T star here in the first component, then you cannot just suddenly transfer the T to that side without star, because that's not allowed. You can, however, do one thing. You can switch the positions of these two components like this. I mean, this property is available to us for inner products in general. So if you switch the places of the components, a complex conjugate comes. So that way you have V comma u T star. Now inside this you can again do what we have been doing. So now you transfer this T star over to the first component, it becomes T, but the bar stays complex conjugate, and then again this bar allows you to switch it back. So that way you get u comma V of T, because this thing, where is it? This thing is equal to this for all u belonging to V, for any u belonging to V. That is why the second component there equals the second component here, which means that the effects of the operators T star star and T on any vector are the same. That is, they are identical. So that's how we have part 1. So next we have part 2, where the beginning is again that same thing. We have V, then for any u belonging to V, this time we consider this. So you see the similarity. We still have u and V, and on V we are applying the operator that we want. Okay, there it was T star star, this time it's the star of S plus T. So first S plus T star changes position, goes to the first component, it becomes S plus T. And then what did we do here? Here we applied the definition of addition of two operators. This is what S plus T means. When you apply it on a vector u, it means us plus ut, the sum of the two vectors us and ut, comma v. But then by linearity, that becomes equal to this, us comma v plus ut comma v. And then again we transfer the operators to the second component. This becomes u comma vs star, but then a star comes with them, on them, and this becomes u comma vt star. And then again by linearity, if you combine these two, you get this, the inner product of u and vs star plus vt star, which by the definition, which means this thing by the definition of addition of operators is again equal to this. the S star plus T star image of V. So we can write the conclusion like this: because of the equality of this inner product and this inner product for all U belonging to V, so this second component equals this second component. The S plus T star image of V is equal to the S star plus T star image of V. But V itself is also, after all, any vector in V. That is why, as operators, these two are identical. So that's how we have number 2. Next, number 3, you similarly try it yourself. But of course, if you still find it difficult to get, you write in the comment section below, then I will do it for you. And finally, we have part 4, where again we have take any V in V, and for any vector U in V, this time we consider this inner product, the inner product of U and the ST star image of V, that is the star of the product ST, that is the operator. So this, as usual, gets transferred to the first component, it loses the star, and then we apply the meaning of the product ST here. What does ST mean? What does it mean to apply ST on the vector U? It means that first you apply S, you get another vector which is US. On that, then you apply T. So that is why we write like this. We re-bracket this entire thing differently. So this is the meaning of this. Now you can transfer this T back to the second component. So it will become T star. And then in the next step you transfer the S also back to the second component. Then it becomes S star. Note carefully that putting this S as S star here means what? It means applying S star on whatever is available there from the previous step, which of course is this vector, and that is why we are putting these parentheses. And again, this means what? Just like this product, this means the T star S star image of the vector V. So equality of this and this for any U belonging to V means that this vector is equal to this vector. But then again, because this is happening for any V in V, this operator and this operator are identical. So that's how we have part 4 as well, and this is where the proof ends. And after this proof, the author mentions that because of this lemma, because of these parts, the star that we see here, that is Hermitian adjoint, is an adjoint. If you go back and see in section 6, 8, I think. Let me just see. 6, 8 means, of course, we are in the 6th chapter, so it's in the 8th section where we have trace and transpose. Towards the end of that section, we defined general adjoint. So this is one example of a general adjoint, Hermitian adjoint.